this concept is ridiculously, stupidly important. Okay? Electronegativity is the ability for an individual atom to grab bonding electrons. Okay? So what you're looking at is the interaction between two atoms. Okay? That interaction comes down to a pair of electrons between them, which we'll talk about when we get into Lewis structures, and deciding where those electrons sit. Do they sit evenly between the two atoms, or do they sit closer to one atom than the other? That's all dependent on electronegativity. Okay? And that has vast implications as far as how individual molecules can interact with each other and how we can make and break bonds. So, organic chemistry, biochemistry, anything in biology, even though they say, oh, you don't need to understand chemistry. You really, really do need to understand chemistry and how those interactions are happening. They usually simplify it down into looking at electronegativity. Right? Fluorine is your highest electronegativity, cesium is the least. It tracks with metallic character, so it's pretty much the same thing, the opposite of metallic character. Your most electronegative is your upper right, which happens to be the least metallic. You'll notice it's not a perfect trend. There are cases where you see some slight variations and some slight exceptions to that. But for the most part, it tracks pretty well with that overall pattern. Upper right-hand corner being the most electronegative. Okay? And when we get into bonding, we'll talk about how we can apply electronegativity to determine the types of bonds and all of that. Okay? The last part in Chapter 5 is looking at this concept of ionic charges. We've already told you that you have to go through and memorize some, so you'll notice that we've got a table that gives you more charges. Okay? And the charges that we're really looking at in this case is not as in-depth as before, but it covers most of them. And you'll notice that there's some weird ones floating in there, like the tin and the lead. I wouldn't worry about those two. Okay? But everything else is kind of important to look at. Okay? This term isoelectronic really just means the same electrons. Right, so what we're looking at when we're looking at our charges and what charge an individual atom becomes, particularly when it moves into a compound, is dependent on this whole, what does the atom have to do to look like a noble gas? Well, what does that mean? Okay, why would... Yeah? Why do our atoms want to look like a noble gas? Okay, we already said they're the most stable, so that makes sense. Okay, but why are they the most stable? That was a harder question. Okay, and that question comes back to electron configurations. Where do our electrons exist within an individual atom? All right, so let's take a look at the electron configuration for helium. How many electrons does helium have? 2. Okay, where does the first electron go? First orbital, which happens to be the s orbital at what energy level? 1. How many electrons can fit into that s orbital? 2. There's my 2 electrons. What we now have is a perfectly symmetrical sphere with 2 electrons in it. Everything looks beautifully symmetric, nice and full, nothing's weird going on with it. So helium is a really stable molecule because of that. There really isn't any place to add an extra electron, because if I add an extra electron, where's that extra electron going? A higher energy state. Well, we don't want to do that if we don't have to. And if we remove electron, we lose some of that kind of balance of having 2 electrons in the orbital, of having it full. Okay, so helium doesn't really want to gain or lose electrons because it loses this kind of symmetrical appearance. What happens if we move up to neon? Neon's the next one, right? Yeah. How many electrons does neon have? It has 10 electrons. How do you know it has 10 electrons? Atomic number is 10, so until we specify a charge, it's going to have the same number of protons as electrons. Okay? So we've got our first 2 electrons. They went into the 1s orbital. That gives us 2 electrons. Where do we put our next set of electrons? We move up in energy, so we move up to the 2nd energy level. And you said S, why S? S is our lowest energy form of our orbital, so we're always going to start with our S. Right? How many electrons can fit into an s orbital? 2. Right? How many electrons do we now have in our configuration? Only 4. Neon needs 10, so we need to dump in another 2, or I can count 6 electrons. Okay? Where do those next set of electrons go? Right? We're at the next energy level, so we have another type of orbital. There's our p orbital. Right, now we run into an interesting question. How many electrons fit in an, sorry, there's no n. How many electrons fit in a p orbital? Okay, 2 answers came floating out there. What were those 2 answers? 2 and 6. Very tricky question. Okay. We can only fit 2 electrons in a single orbital. So the way the question was phrased is where you're looking at a single p orbital. A single p orbital can only hold 2 electrons. For the person that said 6, if you want to volunteer, why did you say 6? You don't have to volunteer. It's not even quite the energy level. If we look at the p type of orbitals, how many orientations are there? There's 3 orientations. Each of those orientations is an orbital. Each orientation can hold 2 electrons. With 3 possible orientations, that gives me a total of 6 electrons. So you have to be very careful with the question that's asked. If we're asking for how many fit in a single p orbital, it's 2. Because all orbitals can only hold 2 electrons. If we're asking can fit in a particular type of orbitals, okay, we're now not asking a single orbital, we're saying within that class. Okay, and within that class, that's dependent on what type of orbital we've got. So for the s orbitals, how many electrons can we fit in the s-type orbitals? 2, and only 2. In the p-type? P-type, 6, okay, because we have 3 orientations. In the d-type, 10, because we have 5 possible orientations, and each of those orientations can take 2 electrons. Is that a question?
Yeah, where are you getting the S and the P?
So the S and the P come from the different, or if you really want the hardcore answer, it comes from the quantum mechanical solve for where an electron can exist. Okay. We assigned different letters to those shapes that came out of it, and that's the S and the P. Okay. From what you need to kind of realize is when we look at the periodic table, we can group our periodic table according to S's and P's. So this first block has only 2 columns. What orbital can only fit 2 electrons? S. This is known as the S block. If we take a look at the next block, and you'll notice I won't include helium in this. How many columns do I have in that? 6. So I'm looking at 6 electrons. What type of orbital can fit 6 electrons? Our p-type. Right? So all those S's and P's and D's are just a classification of what type of orbital can fit there. Okay? As far as directly solving what that orbital is, you're not responsible for it, and you should be very thankful for that. Okay? I'm thankful for that. Beyond that, you kind of just have to accept that that's what it is. And then how they fill, there's 2 ways you can know how they fill. Okay, there was that chart that we put up where you had started with the 1s, then you moved up to the 2s, 2p, and up to the 3s, 3p, 3d. And you did that stupid diagonal line all the way through it. Or you can go through and look at how the periodic table is arranged. We start with hydrogen. Hydrogen, it's there. With 1 electron. Sitting in which block? The S block. Then we move to helium by adding another electron. Okay, and you'll notice helium, I didn't box into the p block for a very good reason. Because how many electrons can I fit into an s orbital? 2. So remember how sometimes we said we could have hydrogen over here by our helium? Sometimes we can see helium over here, because that helps represent its electron configuration. And as far as what number shows up in front of that s, well, what row would we be in? for both hydrogen and helium?
One.
It's the first row, so it ends up becoming 1s. If we move to the second row down, okay, now it's our second row, so we specify 2. It's our energy level. If we look at the first element within that, that's in which block? The s block, so we go with 2s with 1 electron. If we move to the next column over, we had to add an extra electron, so that goes to 2s2. If we move all the way across the other side, now what block are we in? P block. We introduce a new p or a new type of orbital. That's our 2p. Okay, and then we could count across. What was I doing? Neon. 1, 2, 3, 4, 5. Sorry, next row up. 1, 2, 3, 4, 5, 6. I need 6 electrons into it. Okay. The 1s, 2s, 2p works really well, and then even 3s works really well, where we start running into issues when we bring in the 3ds. And now you'd have to remember extra rules. And as far as electron configurations, you will be asked that for sure, absolutely, on the homework. You should be. Yeah? Okay, good. I probably won't ask a question about the d orbitals on the exam, because that is a more advanced application of it. You might see one question, but for the most part, we'll stick up in the 1s to the 3p, because those track immediately off the periodic table. The 3D is a more advanced application. Right? Well, if you move into 151, you're taking a more advanced Gen Chem. You're expected to know how to deal with those d orbitals then. Okay? And you'll go into more examples behind building those. Does that kind of make sense?
Yeah.
Okay, which I know is a wishy-washy answer, because you asked, how do we know what the orbitals are? And I said, just have to know.
I just don't really get why you gathered up those for neon when it comes to it.
So just look at counting it out for getting to neon. Okay? We're going to add 10 electrons in. Our first electron has to go in the lowest energy. So we start with hydrogen, and as we move up to neon, what do we have to do? Well, hydrogen has just 1 electron. That 1 electron goes into the 1s orbital. If we move to helium, okay, it's still in that first energy row, so we put our second electron in. We're now at helium. Neon needs 10 electrons, so we have to add another electron. So we add another electron, but that next electron has to go into the second row, which means we're at the second energy level. So we can slowly just start counting our way up to whatever element we're looking for our electron configuration. And that might be the easiest way to think about doing it. Another, yeah?
Are you going to have like a D block on the test?
I won't ask the D block on the test. Okay, that is my vow. If I do that, you can yell at me. Okay, even in chorus, but you got to do it in chorus. Okay. Alternating sentences.
So we're not going to have the periodic table to look at.
You will have the periodic table. Remember, it's up on the walls, so I can't dismount it from the walls. So not only will it be up on the walls, I will provide on the last page a periodic table. I meant to do that on the first test, and I just forgot. So the very last page will have a small version of the periodic table on it. Okay? Well, remember, we're chemists. Everywhere we go, we have a periodic table. Other questions? Yes?
You talked about abbreviations by starting at a specific element.
We'll get into that when we go beyond neon here.
Okay.
Okay? And actually, we can do it with neon here in a second. Back to our question, why do things want to look like the noble gases? Well, what happened to our energy shell? How many more electrons can fit into the second energy level? None. So if I add an extra electron, I now go up in energy. I go up to my third energy level. Well, that's bad. I'm going up in energy. I want to stay as neutral and low energy as possible. What if we removed an electron? I wouldn't go as far as unstable, but you got the right idea. It's not symmetrical. Okay? Now, if we looked at our p orbitals, one of them is missing an electron, where the other ones all have 2 electrons. So now it's not symmetrical. So our noble gases are really special because they've completely saturated the electron configuration, or that energy level for electrons. That full saturation then means they don't want to move up to the next energy level, and they don't want to move down because then they lose symmetry. They stop looking pretty. So our noble gases are pretty awesome in that respect, and that's one of the reasons why they don't react. Because to react, we have to share electrons. Well, if neon doesn't want to get rid of electrons or take more electrons, is it willing to react? No. Okay? So, some abbreviations. You'll notice that I left helium's configuration in red. So we started with helium as 1s2. Okay? For this structure, for neon, we can go through and abbreviate this and say, well, that 1s2 is really just the configuration for helium. So if I want the configuration for neon, it's the configuration for helium plus the 2s2, the 2p6. So all I'm trying to do is now just abbreviate the amount of work I have to go through and do. Did that really save me any time in this case? No. I wrote 1s2 versus helium in brackets. But what if we jump to argon now? Let's see, where do I have some space? Let's drop the argon just kind of in between. Okay, if we're going to build up argon, go back to where we were starting with how can we put in our electrons. We go for our very first electron goes into what energy level? Our first energy level, so 1, what type of orbital? S. How many electrons do I want to put into that orbital? Well, depends on how far I want to get. I want to get to argon. So I'm going to saturate that orbital with electrons, 1s2. That only gets me to helium. I want to get to argon. So what do I need to do? Next energy level. The orbital available to me? 2s. Okay? I want to saturate that one, 2 electrons. The next orbital available to me, the p, which can fill 6 electrons. Okay? That still doesn't get me there, so what do? Next energy level. Okay? 3s. Next orbital. Not a capital S. Try that again. The 3p. And we'll put 2 electrons into the s, and how many electrons do we want to put into the p for argon? 6, because it's in the 6th column of our p block. That was a lot of stuff to write out. Okay? That configuration is the exact same as we had for neon, plus a bunch of extra stuff.
Well, you didn't add the 1s2 in the neon.
I did have the 1s2 in the neon. You'll notice I wrote helium instead. I erased the 1s2 because helium is 1s2. And I'll end up doing the exact same thing here. The 1s2, 2s2, 2p6 is the configuration for neon.
Good neon.
Did I save myself some time now?
Yep.
Yeah. Okay. I could now get away with writing a little bit less. Okay, so what we're saying is within those brackets that we're looking at the electron configuration for whatever that element is plus some extra terms. And you'll notice that when we go through and use this symbology, putting in those brackets for that element, the only elements that we'll include in those brackets will be the noble gases. Because we're always adding something extra to the noble gases to get to our electron configuration. Okay? Could we be really cheaty with our argon configuration? Sure, why not? Our argon is a noble gas. Isn't that the electron configuration for argon? Okay. Yeah, would we ever ask or give you a multiple choice option to be able to do that? No. Okay, the idea is to prove as much as you can about it. Okay, kind of makes sense? Yeah.
Do we have to simplify it?
You do not have to simplify it.
Technically, you're not gonna go past the D.
I'm not going to go past the D's anyway, so we're not even going to worry about it. Yeah. When you get to the homework, you will have to, and you will probably need to take a look at some more practice problems within the textbook to get a feel for what's happening with those. But you're going through the same filling system as outlined in that table, okay, which I wish I had in the slideshow, but I don't. Okay? So let's take this now back to where we're trying to get what's going on with isoelectronic and all of our charges. Okay, the first one that we're going to take a look at in this case is I want to look at the electron configuration for lithium. Okay, let's take a look at just lithium metal. What's the electron configuration for lithium metal?
1s.
So we'll start realizing that lithium has 3 electrons. We need to add electrons into our orbitals to get up to lithium. So we'll start at our 1s, 2, and 2s, 1. We could go through and abbreviate that as
Helium.
helium and our 2s1. Okay? Doesn't shorten our work that much, but it can help us out. So that is our electron configuration for lithium. What is our electron configuration for lithium ion? So lithium ion in this case is Li+. How do we get positively charged? Why electrons? Well, I could add a proton. That makes it more positive.
Changes the atom.
Okay, remember, there's 2 things that carry charge, the protons and the electrons. If we change the protons, is it lithium anymore? No. So the only thing we can change are the amount of electrons. So what happens to our electron configuration for lithium? Now, how many electrons do I need to explain?
2.
Only 2 electrons. So I'd start again at my lowest energy level, 1s, 2. Okay. Also known as helium. The lithium ion electron configuration is isoelectronic to helium. Okay? Said again, our lithium ion electron configuration has the same configuration as a helium atom. That's all isoelectronic is asking. Okay? Why might lithium lose just 1 electron? Why might its charge always be +1? What happens to its electron configuration if it loses an electron? Looks like helium. What did we say was special about our noble gases? Why were they stable? We've saturated our orbitals, okay, within that energy level. Nice and symmetrical, beautiful looking. So our lithium atom wants to look beautiful, so it'll change its structure however it can to still stay lithium, but now look like the noble gas. Helium happens to be the closest one. Could it have done something else? Is there another noble gas it could have looked like? Could have looked like neon. To do that, what would lithium have to do?
You have to gain 6, 7 electrons.
It has to gain 7 electrons. Well, which is easier, losing 1 or gaining 7?
Losing 1.
Losing 1. So what ends up happening? Our lithium will give up 1 electron as opposed to gaining 7 electrons, because it's a lot easier to give up that 1 than to steal 7. Okay? What happens when we look at sodium? Let's erase everything again. Let's shift to our sodium. What's its electron configuration? 1s2, 2s2, 2p6, 3s1. Also, it's the electron configuration for neon plus a 3s1 electron. What happens if I'm going to try and predict sodium's charge? Okay, so now let's look at that electron configuration. If sodium's going to form a charge, what's its most likely charge to be? Positive 1. Why?
Because it's going to want to lose that electron.
If we lose that 1 3s electron, its configuration becomes neon. So sodium is now happy. So what's the most likely charge for sodium? Positive 1. What did we tell you to memorize? Positive 1. You'll notice that all of the elements in that column will have the same type of configuration. A noble gas followed by the energy level S1 electron. Every single one of them. Test it. And if we look at what's going to happen for their reactivity, the easiest way for them to look like a noble gas is to get rid of that 1 electron. What happens when we move to the second column? Let's switch this up to, what are we looking at? Magnesium? Let's do magnesium. So it'll look like neon, the noble gas above it, plus a 3s2. Okay, if we had to predict its charge, what might be its most likely charge? +2. Why?
It's still gonna wanna get rid of the 2 electrons.
We're still trying to look like a noble gas. So it can either lose 2 electrons to look like neon, or it can gain 6 to look like, what's the next one? Argon. Which is easier? Lose 2, gain 6. Lose 2. Okay? As we continue to move through our periodic table, let's jump to aluminum. Electron configuration for aluminum. We can look at the noble gas in the row above it, neon. Now we'll drop to our third energy level, 3s1, 3s2, 3p1. Alright, so there's our electron configuration. So we again ask the question, for aluminum, wanting to look like a noble gas, what does it have to do? It can either lose 3 electrons to look like what? Neon, or gain 5 electrons to look like argon, which is easier. Lose 3. What's the charge that we tell you to memorize for aluminum? +3. You don't have to memorize it if you understand where the electrons are going. Okay? If you don't understand where the electrons are going, what do you have to do? Memorize it. Feel free to take whatever choice you want. Okay? Particularly if this is the last chemistry class you have to take, probably easier just to memorize it. If you got to take more, start learning your electron configurations. What happens when we jump to phosphorus? You'll notice that we don't stop at silicon or carbon. So let's jump back up to nitrogen now, just because, well, no, we can stick with phosphorus. I lied. Phosphorus. What's its electron configuration? So the noble gas above it is neon. Then we look at its energy level. We've got the 3s that has to fill, and then we have to fill in how many more electrons into the p. We need 2 more electrons from our configuration. We have the 3p3. Okay? What does that then mean? We look again at our balances. Whoops. We're looking at either neon or argon again. What does phosphorus have to do to look like neon? It has to gain 3 electrons. No, sorry, look like neon. It has to lose 5 electrons. Or, to look like argon, it can gain 3 electrons, which is easier. Gain 3 electrons. So what charge do we predict for our phosphorus? -3, because it picked up 3 negatively charged species. And what charge do we tell you to memorize? -3. The electron configuration tells you the charge. You'll notice that there was a column missing. Let's take a look at carbon's electron configuration. I'm going to drastically simplify our configurations here. So carbon. Configuration is 1, S2, 2s2, 2p2. To look like helium, what does it need to do? It has to lose 4 electrons to look like helium. So we get rid of this chunk and we look like helium. Or we can gain 4 to look like neon. Which is easier? It's the same. So what charge do we have you memorize? We don't. Why not? Because it sits right in the middle. It can go either direction. Okay? As far as what these ionic charges are. Yeah, pretty much. The semi-metals kind of fall along that line. And you'll notice it's diagonal, and it's diagonal because it gets more complicated as you add in the d orbitals. Okay? So we spent a lot of time talking on this, really going around that idea of isoelectronic. All right? So when we're looking at our electron configurations, what we're trying to do is just look like a noble gas. All right? Get to the noble gas the quickest as possible. You'll notice when we looked at lithium, the noble gas we tried to jump to was helium. Okay, but that looks really far away, even really far away from neon. So what you can do is take your periodic table and actually turn it into a cylinder and skew one off. And when you skew that one off, lithium gets right next to helium. All right, so it has to do with that electron configuration, how you can bounce back and forth between those. Questions? Is it way, way out there, or are you guys okay with that? Okay, and I can accept that. That's 50%. It's passing, right? So, what I've got now is a quick summary of Chapter 4, and a lot of people have been kind of panicking on what kind of questions to see. So what I posted was a Chapter 4 summary of all the big topics that came out of Chapter 4, and I followed it up with some kind of hardish exam questions. So, Chapter 4, we got some cool scientists that popped up into this. What were those cool scientists? Because you all memorized it already, right? Yeah, I think I heard all those names. What did Dalton do? He was all the atomic theory, so you have to know what his atomic theory is. Thomson? Ish. He really discovered that we have subatomic particles. Okay? So that means protons, electrons. Okay? That's what Thomson gave us. He didn't actually tell us where they existed. He just knows, hey, they exist. Okay? We have something smaller than atoms. Millikan, it's a harder one. That was only in lecture. Looking at our charge on our electrons. Curie, okay? She really got nailed down radium. Okay, radium was the one that allowed Rutherford to then discover the nucleus. Okay? So understanding what each of these scientists was responsible for is going to help you kind of transfer kind of exam questions. So you can fully expect to see an exam question along those lines, and as you can hopefully clearly see from here, all that's going to be is strictly memorization. You either had it memorized of what that scientist did or you didn't. I can't ask anything beyond that. We end up with our subatomic particles, protons, neutrons, electrons. What questions could I ask about protons, neutrons, and electrons? I can ask something about charge, and we can also ask something about mass. Okay, what's the mass of a proton?
1.
Okay, 1 is the answer that I would expect you to come up with. The official answer was like a 9.9 times 10 to the negative something or other, some crazy weird kilogram value. What I expect you to know is the ratio between these. So if the mass of a proton is 1, what's the mass of a neutron? 1. The mass of an electron? 0. Okay, it has virtually no mass. And then, I don't know if I said it, do we say charges?
Yeah.
Okay. The wave nature of light. Okay, really all we're getting out of the wave nature of light is this concept of continuous versus discrete, okay, or quantum. Okay, what does that mean? If we look at a rainbow is continuous. If we look at an atomic line spectrum, it is discrete. We have lines. Okay, so recognizing the difference between those. Okay, and the next part of this is Bohr took that atomic line spectrum and actually gave us the existence of our electron orbitals. So he was all about being discrete. Orbitals are electron homes, where they exist. Okay, that's where we get the different orbital types, which I don't remember if I put on here. Let's see. Oh, I didn't put those on here. So within our orbitals, we have different types. What are those different types? S, P, D are the primary ones we talked about, but you are correct, we do have also the F. Right? We didn't explicitly talk about the F, so what kind of questions might you expect to see about the F? Probably none. Good guess. Right? Subatomic particles. This is where electrons really come into more play because we're describing where the electrons exist within those. We run into two possible discussions, either configurations or the valence shell. The valence shell is going to become really important when we look at bonding. Configurations is looking at what we just went through. Okay, what are all the electrons that go into an individual structure? So if we looked at hydrogen, the configuration for hydrogen is 1s1. What's its valence? 1s1. Our valence is the outermost energy shell. With hydrogen, there's only one energy shell, so it's the same. But what happens if we jump up to lithium? Lithium's electron configuration is 1s2, 2s1. What's its valence shell? 2s1. We only look at the outer. Okay, so that's our difference between our configurations and our valence. So, some hard chapter 4 questions. What orbital has the cloverleaf shape? What is the S shape? It's three-dimensional. Sphere. Okay. And our p orbital has the dumbbell shape. So the cloverleaf shape, D. We don't have to worry about F, so we don't have to worry what those look like. Okay. How many electrons fit in a p orbital? Kind of a tricky question. There's our 2, because we're referring to a single p orbital. How many electrons fit in the third energy level? Ugh. So the third energy level, we're saying row 3. So what orbitals do we have in row 3? Our S, our P, and our D. Remember, as we go up in energy, we increase the number of types of orbitals. In our third energy, we're going to have 3 possible types, S, P, and D. How many electrons fit in the S type? 2. How many electrons fit in the P type? 6. Why 6? There's 3 orientations for our P type orbital. How many fit in the D? 10. Which means our total comes out at 18. Can we find that on the periodic table? Okay. Kinda, yes. We have to remember that our D is part of the third energy level, even though our D first shows up on our periodic table in our 4th row. Okay. But we could go through and just count the columns across our periodic table and we'd end up with 18. Okay. Electron configuration for titanium. Well, that was a bit mean. You can do it anyway. Okay. Start the long way. 1s2. No, you started the long way. 2s2. We'll see. What's the next one? Why 4s and not 3d? Our periodic table is organized according to its fill. As we go across, 1s1, 1s2, 2s, 2p, 3s, 3p. Next row starts at 4s.
Will you just ask, like, can we just go argon?
We'll get to that in a second. 4s what? 2, 3d, 2. Okay. So this has to go, and this is why the transition elements I'm not going to ask a lot of questions on. Okay? Because we start jumping to the 4th energy level before we finished out the 3rd. Okay? And we did talk about this. The reason why is that once we get up in those high energy states, the difference between those orbitals is very, very small. So what we end up doing is filling a smaller orbital to get symmetry before we fill the other one. Okay? That information on how we fill is given to you. Where is that information given? It's on the periodic table. The periodic table tells you how to fill these. Okay? So you follow each energy level through. The one place that you have to add is that your scandium, your first transition element, is in the 3 energy level with the d-type orbital, even though it is offset by 1. Okay, why is it offset by 1? Because we're trying to explain the electron fill pattern for our electron configuration. Okay? So you do have to bring in some interpretation. All right, that was an awful lot of writing out to do. Could we go through and shift that to something else? We could go up to the previous energy level and look at what noble gas is there, which is our argon.
I thought you said it was up.
And now up 1 energy above it, so that'll go up to our argon.
So wouldn't it be neon?
That's not the energy level directly above it. I know.
Well, if it's moved up.
On our row. So that's where we're going to have to apply it, is based off of our rows. You can go up to neon, but then you're still going to have to backfill in the other 8 electrons to get up to argon. And what's the difference between argon and titanium? The 4s2 and the 3d2. Both of those electron configurations work. Yes?
So if you finish up your 3D, like if you went to 3D10,
Mhm.
and the next level, would that be 4P, all the way to 6? 4P?
I don't remember the exact fills, but it's something like that.
So
You
it's
do end up
P
skipping.
into P again?
Yep.
Okay.
So if you look it out far enough, you can actually see that you'll see more of this swapping of those energy levels. Okay? Again, one of the reasons why I won't ask questions about transition metals, because it's more advanced than you need to be. How many valence electrons are there for carbon? So to figure it out, carbon's electron configuration. Our valence electrons looked at what? The outermost energy level, which is our second energy level. Carbon has 4 valence electrons by totaling those numbers. Okay? Questions on that? Now you all seem super excited about titanium. Should we go back to titanium? Should we try another transition element for electron configurations? Let's make it a step further. Let's do gallium. Okay, give you a couple seconds here to go through and build your gallium electron configuration on your own. So if we look at the valence shell, we are concerned about our outermost shell, which is the 4 energy level. Let me underline those. Which means we have 3 electrons in our valence shell. Okay? Oh, it's not buttoned. What's the shorthand version for this? We look at the previous row. Noble gas is argon. What extra electrons do we have? Our 4s2, 3d10, and our 4p1. Okay. What's the valence electrons? What's our outermost energy shell? The 4. The energy level is 4. How many 4 energy levels electrons do we have? 3. One last way that we could go through and check this to verify that we did it right. 2 plus 2 is plus 6, plus 2, 6, plus 2, plus 10. How many electrons did we put into for gallium? 31. What does that mean? We did a darn good job. We've accounted for all of those electrons. What happens if you total it up and you don't get the 31 electrons? You missed something. You'd better go back and fix it. Okay? On an exam, how do you go back and fix it? It's a good question for exam abilities. If you go through and check a question and find out that something doesn't add up, what should you do?
Start again.
Guess, move on. You've already spent your allotted time doing that one question, and you got it wrong. Okay? If you continue to spend time on that question, you're now spending twice as much time on that one question when you could have moved on to something else that maybe you would get right. Okay? The only time where you can go back, if you've gone through and done a check and verified that it's wrong, okay, mark it. When you finish the exam, you can come back to it and say, okay, what did I do wrong? And when it's what did I do wrong, it's you do the question again. You don't touch your previous work. Why do you not look at your previous work? Because it was wrong. Okay? The odds are that you're going to see your mistake very, very slim. So redo the question. Does that take time? Absolutely. That's why you come back to it later. Right? After you finish the rest of the exam. Right? Questions? Excited about it? So much for talking about bonding. Chapter 5 summary. Okay? I'd rather spend some time reviewing it and making sure you got this right. Mendeleev, so we get another famous scientist coming out of this. You can correspond his name to periodic table. That's pretty much all you need to know. Okay? The other big thing that Mendeleev brought out of this was predictions. So if I give you a bunch of properties for an individual element, say a bunch of different densities, okay, you should be able to predict a missing value. And we did an example of that in the slides already. Trends. Okay? The big one that I highly encourage you to remember is your electron orbitals. So when we look, we've got the S block, the D block, the P block. Okay? That trend is really, really important because that can get you electron configurations. It can also get you charges if you didn't memorize the charges. Okay? So it can really help out if you know those general trends. Okay? We can get chemical and physical properties. This is out of the predictions. Atomic radius. Okay? So if we move down a column, what happens to the size of an atom?
It's larger.
Gets larger. Why? You're putting electrons, more electrons in, but where are those electrons going? Into a higher energy level, which means it's further away. So as we move down a column, the electrons have to get further and further away from the nucleus. If they get further and further away from the nucleus, what happens to the size? It gets bigger. That trend makes sense. Left to right, what happens?
It gets bigger as well.
That one's weird. What happens left to right? It gets smaller. Why does it get smaller? Where do the electrons go? As we add an electron from lithium to beryllium, where does that next electron go?
Higher energy level?
Does it go in a higher energy level? The electron configuration for lithium was 2s1. Electron configuration for beryllium? 2s2. Did it go to a higher energy level? No, it went in the exact same energy level. So what happens to the size based on just where you're putting the electrons? Nothing changes. Uh-oh. Okay, so we got a little bit better. We're getting closer to it getting smaller. What else changes as we go left to right on the periodic table?
The mass of the nucleus.
Yes, the mass, sort of, but to increase, okay, as we go from lithium to beryllium, yes, the mass increased, but there's something more important. The number of protons changed, which means in the center of that nucleus, it has become more positive. But we're putting electrons the exact same distance away. So if one of our magnets becomes stronger, what happens to the attractive force? It gets pulled in. So when we go left to right, we're putting the electrons at the exact same distance away, but we're making our nucleus stronger. That pulls the electron ever so slightly a little bit closer. So when we look left to right, our radius decreases because our nuclear strength gets stronger. Okay, so that one's an odd explanation, and that really only comes from looking at the electron configurations. We're putting our electrons in at the exact same energy level. Okay? Ionization energy. What was our general trend? Okay, and with the ionization energy, the only one I'll expect you to do is know the trends. So the ionization energy was what? The ability to grab and remove an electron away. Take an electron away from an atom. If we get really, really big, where are those electrons? Really far away. So if we put down a dollar bill right here, we're going to duke it out. Here's the dollar bill. It's my dollar bill, by the way.
Okay.
Here, you can step it up. Okay. We're going to fight for that dollar bill. You ready? Yeah. Okay. What happens as we look at our ionization energy? What happens to the distance between me, the nucleus, and my wallet as my electrons? Better give it back. Ready?
Don't hit your hip.
Yeah, I'm not gonna. As we get further and further away, what happens to the ionization energy?
Your hold on it isn't as strong.
I can't hold on to it as tightly. It's a lot easier to pull that electron away. Okay, so as we get bigger, the ionization energy gets smaller because I can't grab it quite as quickly. If we look left to right on the periodic table, what happened to our size? It got smaller. Okay, so we could use our smaller to help us with the ionization energy. If it gets smaller, what happens to the distance between me and my wallet? It gets even shorter. Okay? If you don't remember that, what happens to our nucleus? Our nucleus is getting bigger. Okay? Getting stronger. So I'm already pretty big, but if we turn I became the Hulk, and we're at the same distance. You really want to start that fight? Okay. So as we move left to right, we have a stronger nucleus. It's going to be harder to pull that electron out. Okay? Last thing is our ionic charges. That's our chapter 5. So these are some pretty hard questions. I'm going to kind of whip through these because I do want to get into bonding a little bit. Okay? Rank the following atoms according to ionization energy. Ranking questions are favorites for test questions, particularly in chemistry, because it forces you to really understand what's happening within it. You notice I added an extra wrinkle to this question. What's that wrinkle? Also testing nomenclature. You need to know what Na is, you need to know what gallium is, or Ga, but that's off the periodic table, that's easy enough. You also need to know what the symbol is for carbon so you can compare it to our table. The next thing that you'll look at is that those are not all in the same row or in the same column. So how could you come up with a way to rank them? Pick any two and find what's common between them. So sodium and carbon, what is common between them? Wish I had a periodic table that I could draw on. All right, so what we're saying is we look at carbon. Where's carbon? Carbon up here, and we've got sodium over here. There are two elements that are common between carbon and sodium. Lithium and silicon. Okay, so pick one of those. What's the relationship between carbon and silicon when it comes to ionization energy? Where are they? In the same column, which means higher up we are in the column, the higher the ionization energy. So silicon is lower than carbon. Silicon versus sodium. They're in a different row. Which one's higher than the other? Or different column, I mean. Silicon has a higher ionization energy than sodium because it has a stronger nucleus. So we said carbon was more than silicon, and silicon is more than sodium. What does that mean about the relationship between carbon and sodium? Sodium must be lower than carbon, or carbon's higher than sodium. You've now ranked two. What do you have to do? Add the third into that equation. So pick gallium and compare it to either carbon or sodium. Okay, and see if you can slowly piece together that ranking. Okay? Do not look at it and say, oh, the answer must be sodium, carbon, gallium, or gallium, carbon, sodium. Okay? Who knows until you actually define it? So go through and pick any two for any ranking question. Pick two, evaluate those two. Slowly add more into the problem. Okay? Electron configuration for nitrogen, electron configuration for oxygen. Okay? Both of those you should be able to go through and do. Here's how I could ask the trick question with the ionization energy. I now tell you nitrogen has a higher ionization than oxygen. Given that information, you need to explain why. Well, we just talked about what happens with our ionization. What did we need to look at?
Ability to pull electrons.
The electron configurations. Once you draw out the electron configurations, you would then evaluate why you see that difference. If you don't look at the configurations, does that match the trend? We said as left to right on the periodic table, what happens? Increases. But nitrogen is higher than oxygen. Does that follow the trend? No, which means you have to understand where the ionization energies are coming from. That goes back to the electron configurations. Stupidly hard question. But if you want an A, you can expect to answer that question correctly. If you don't want an A, don't worry about it. It won't affect your grade. You can pick up points elsewhere. Okay? Explain why the ionization energy for neon is so high. This would be an easier question. A couple answers I'd expect on this. We can go according to our trend. The trend says it goes higher as we move across the periodic table. Good, solid answer. All right, that doesn't show an understanding of what's happening with it, but it shows that you have the trend. What's the real explanation? Look at the electron configuration and you'll notice they're all full. Nice and symmetrical. It doesn't want to lose that symmetry. Okay. What charge does silicon need to be isoelectronic with any one of those elements? So for argon, to be isoelectronic with argon, what does silicon need to do? Where's silicon? Number 14. Where's argon? Number 18. What does silicon have to do to look like argon? It needs 4 more electrons. If it gains 4 electrons, what happens to its charge? -4. What if we want it to be isoelectronic with aluminum? All right, we look at the periodic table. Oh, it's the other direction. We have to lose an electron. So the charge of silicon would be to look like aluminum? +1. It's the balance of the protons and electrons. Okay? And now 10 minutes to do an entire chapter. It's not going to happen. Don't stress. Right? Here's some random questions from the Chapter 7 book. This is not your homework. Remember, your homework is online, Mastering Chemistry. These are problems that I happened to look at in the textbook and I thought were reasonable for going through and giving practice. So feel free to take advantage of those. Okay, sorry, you need a picture of that? Okay. Chapter 12, we're looking at chemical bonding. You have these PowerPoints. They are posted on Canvas. Well, we're looking at chemical bonding. So we're going to take 2 atoms. Did I just do that?
No.
We're going to take 2 atoms and we bring them near each other so that they form a bond. What's the first thing that's going to interact between those atoms? Okay, the electrons. Which electrons? The valence electrons, the outermost energy level electrons. So when we're looking at making a bond, what we're concerned about is how those valence electrons interact with each other. Okay? That's the characteristic of our bond. So what we need to be able to do is know what our valence electrons are. If we don't know what our valence electrons are for an individual atom, we aren't going to be able to solve this problem. Okay? Next question. Would we expect all bonds to be the same? Okay. Well, if we just looked at these 2 pictures, are the colors all the same? No. In the first case, we're taking 2 atoms that are identical, nitrogen and nitrogen, and we put them near each other. In the second example, what are we doing? Different atoms. If the atoms are different, what does that mean about the energy of their electrons? They're different. What does that mean about the energy of the bond where we're looking at the electrons? It's going to be different. So because we can change the energy level of our electrons, we're also going to change the types of interactions that can come out of it. The primary interaction we're going to be concerned about in chapter 12 is bonds. Okay? You're actually already aware of some bonds because you had to go through and name them in chapter 6. Okay? What are the two primary classes for bonds? Ionic and covalent. Okay? So chapter 12 goes through and adds some extra information to this. When we're looking at ionic bonds, most commonly we're looking at a metal and a nonmetal. In our covalent bonds, it's two nonmetals. Okay? And we'll use slightly different naming when we go through and talk about these, which bothers me, but that's the way it is. Ionic bonds get represented by formula units, and covalent bonds get referred to as molecules. Okay? I'll call them molecules in both cases because I think that distinction is pretty meaningless. Okay? Are all nonmetal covalent bonds the same?
100%.
All right, we got two compounds down at the bottom. And actually, let me help with this. Little nomenclature practice. Sort of nomenclature practice. That first compound, H2O, is water. Okay, it's a covalent bond, so you should be able to name that. What's the name for that? Don't tell me water, you just told me that. Dihydrogen oxide. Because there's two hydrogens and one oxygen. We can call it dihydrogen oxide. How about the next one? Hydrochloric acid. So are all bonds the same? Well, let's think about it this way. Okay, I like to do this for organic. Not very nice, but it's appropriate. Okay, we have two containers up here. One full of water, one full of hydrochloric acid. Guess what we're going to do now? Splash them on you. Which one are you particularly concerned about?
Hydrochloric acid.
Hydrochloric acid. Why?
Because it'll burn you.
It's going to burn you. Why is it going to burn you? It still has a covalent bond. Are there differences in covalent bonds? Yeah. There is a dramatic difference. Both of those have covalent bonds. One burns the crap out of you, one you can't live without. Okay? So there is differences within each of these bond structures. Okay? And that does make this discussion a little bit more challenging, but that's what makes it interesting as well. When we're looking at our ionic bonds, okay, I've come up with this sort of weird analogy with little kids. Might call them the 2-year-olds of bonding. I've never had a 2-year-old, so I don't know, but I heard the terrible twos. 2-year-olds are horrible, right? Okay? They do not share. So what we're looking at within an ionic bond is that we see a complete transfer of electrons. Transfer is bolded because that phrase shows up on tests. If we look at a bond where there is a transfer of electrons, that is characteristic for what type of bond? An ionic bond. Okay? So what we're looking at is a formal positive charge and a formal negative charge. The positively charged ion is referred to as a cation. The negatively charged ion is referred to as an anion. Okay? Because we've got these charges oriented around, we now organize our structure to balance out those charges as much as possible. So near our cation, what do we expect to see? Lots of anions, because we want to neutralize that positive negative charge as best we can. So if we look at our crystal structure, or if we look at a larger structure, you'll notice that we see a very alternating pattern between each of our elements, or each of our ions. That's because we're trying to neutralize that charge. Okay, or the molecule itself is trying to neutralize that charge. We can also look at ionic radii. What happens to the electron count, okay, for our atoms in sodium chloride? So let's kind of predict what might change here. Okay. Sodium is our metal. What do our metals do when they pick up a charge? They lose an electron, so they become, that one would become Na+. What happens to the chloride? Gains an electron, so it becomes Cl-. What is that going to do to the radius? So let's look at the electron configuration for sodium. We've got neon plus a 3s1 electron. What happens when I move to sodium ion? It becomes neon. Which is bigger? Neon or neon plus an electron? Neon plus an electron is bigger. So if we're going to predict something about the cation size, what happened to it? It got smaller as we went from the metal to our ionic compound. So we might predict a relatively small cation. What happens when we look at our chlorine? Our electron configuration for chlorine is neon, oh my gosh, 3s2, 3p, 5. When we go to it becoming chloride, what happened? Gained an electron, so it went to neon, 3s2, 3p, 6. We put that electron into the same energy level. What would we predict to happen to the size?
Same size.
Same size or smaller. But when we looked at that trend with our atomic radius, what happened? We were looking left to right on the periodic table. We increased the amount of protons in the nucleus. When we moved from chlorine atom to chloride ion, did we change the number of protons? No. So that electron is now going into the same energy level, but the nucleus doesn't have more charge to hold it. So what happens to the size? It gets bigger. So if we look at an image for our sizes, we see a complete swap in the sizes when we move to our ions. Okay? Our anions will get bigger, our cations will get smaller. All right, and we will pick up there on Thursday.